Hi, so this is a video about slide set number 1. I'm going to divide the slide set into 2 videos because shorter videos are better than longer ones for obvious reasons. So this video is going to cover slides from 1 to 12 in the slide set number 1. So let's go and see where we download this thing here. So slide set number 1. Note that I'm updating the slides as I go, so it's always better to re-download them if you want to study or follow the videos. So if you download the latest version here, open this like this, and then there we go. Okay, so this slide set is starting off with the structure of a C++ program. As you might have seen, or you might know, it seems that a C++ language is very similar to the Java language. It's kind of deceptive. Has many reasons why a C++ program is different in its structure and especially how it's compiled. So that's what I'm going to try to address in this first part of the lecture. So in a C++ program, particularly, there are classes, which includes methods and so on. So just like what you had in Java, except that in C++ you have this notion of a free function. So essentially your methods in a Java program are functions that are embedded in a class. In C++, you're allowed to have functions that do not belong to any class, which are called free functions. For example, your main function, which is the starting point of your entire program, is one such free function. So any valid C++ program should always have one and only one main function. Along with that, there also comes the notion of compilation unit, which is very important to understand if you want to figure out how your programs are actually compiled. This goes hand in hand with the notion of including files across. When you write a certain program or a certain file, you can include other files, much like when you have import in Java, but the concept is a little bit different. It appears to be the same, but it's technically very different, especially in how or what it means when the compilation process is running. So what is C++? C++ is essentially, as I mentioned before, it's a superset of C. So what that means is that any C program is a valid C++ program. So if you have a C program, you can compile it using a C++ compiler. There are subtleties that make it so that it's not exactly the case, but that's the general concept. So like in a C program, the driver of your entire program is the main function. The main function is where it all starts. In Java, you also have a main function, which happens to be a member function of one particular class. And then when you execute that class, then it starts by executing the main function of that class. There's no such thing as in C++ because there's no main, the main function is a free function. You cannot have a main function inside of a class. So in C, you also have data structures. So basically in C also you have functions, but they are all free functions. In C++, you can have free functions such as in C, but you can also have functions that belong to a class. In C, you had data structures which were not classes. So that's basically a data structure. As we will see later, data structure in C is called a struct. So it's basically an aggregation of other data elements that you put in one data structure. Okay, so because C++ is an object-oriented language, then what it does is essentially it takes some of these functions and then encapsulates them inside of a class, okay, which makes then some functions becoming members of a class. So the main function is a free function, not a member of any class. So very important to make that distinction between C++ and Java. It is still a main function, but should not be a member of a class. And you can have only one. You must have one and only one main function defined in any program. If you define more than one main function, it's basically going to, the compiler is going to tell you that you have a redeclared main function or redefined main function. So here's a first example of a C++ program. So sometimes when I give examples, it's going to jump ahead. There's going to be concepts I did not cover yet. Well, that's part of what it is. So here basically my program is composed. This is a single file program. This is what I'm going to argue here, that yes, you can have a program that is stored in whose code is stored in a single file. That's this example here, but we're going to soon realize that it's not practical to have any program that is whose code is always in a single file. But this is this kind of example here. So in my file, I have the definition of my main function. Note that this main function is not declared inside of any class, so that makes it a free function. So my main function here, what does it do? Basically, cout is an object that you can output to, so that's called a stream. We'll cover that in lecture number 3, or slide set number 3. So essentially here, what you do is you output to the console. So you output some strings to the console, and then cn is essentially the keyboard from which you extract some values from the user using the keyboard. And depending on what value that the user entered on the keyboard, then you will print either this to the console, you will output this or this, okay? And then eventually after this is done, you return from the main function. And of course, when you return from the main function, that makes the program finish execution, okay? Now there's other things here like hash include. This is sort of like the equivalent syntactically speaking, it looks like it's the same as an import in Java. That's the same concept, but it does not have exactly the same meaning or operation in C++. So yes, here you are importing, which in this case in C++ is called including. So you go hash include Iostream. Because you are using cout and cn, which are defined in a certain library, which is called Iostream. So basically, if you want to use cout and cn, you must hash include Iostream. And then here, this is the notion of a namespace, which I will come to later in the second part of this lecture. Essentially here, I'm outputting things to the console, reading from the keyboard. If I want to do this, then I must use Iostream. The cout and cn are essentially streams, which I will explain again in lecture number 3. Now, this was a very simplistic program that is included in a single file. If you want to write more complex programs, normally you should write multiple files, okay? For example, this single file here is actually relying on another file that contains code, which is the Iostream library. So right from the start here, you see that even this program is very simple. It is relying on code that is written in other files. So C++ itself, the basic core language, is you can only write very simplistic programs if you don't want to use libraries or other files, okay? So the C++ language itself only defines some syntactical structures, but it has very limited capacities. If you want to do something more interesting, you have to rely on either libraries, and when you define your own programs, well, you have to somehow create modules if you want to have reusability and things like this, which I will mention later on. But most programs require the use of libraries, which are other files. So it's almost impossible to write a program of a certain capacity or size that does not use any other file. So you should know how to include these other files as you're compiling a program that relies on things that are defined in other files. So that involves, yes, the compiler. So you're basically instructing the compiler to go fetching another file and then compiling this other file as part of the compilation of the file you're currently compiling. So this inclusion actually happens both at compile time, but if there are some things which are declared in the files that you are including, but not defined, as I will point out later, then the linker will come in and actually try to resolve these names across the different compilation units. So that's why it's important to know what is the notion of a compilation unit if you want to understand how all this thing works. So unlike in Java, a single C++ file can contain many classes, for example. So in Java, you define a certain file, and the assumption is that a file contains one and only one class, okay? So there's a one-to-one relationship between a class and a file in Java. In C++, you don't have this one-to-one. In C++, you can have a file that does not even declare any class, and you can also have one file that contains, that declares more than one class, okay? So that leads you to have an additional design consideration, which is called physical design. So if you have, say, 10 different classes in your implementation, then you have a choice to put all these classes in one file or to separate these classes into different files. So that's an additional decision that you have to make compared to what you have in Java, where you have a one-to-one relationship, okay? It's called physical design. That allows for more possibilities. So you can define modules. Essentially, you define one file, implementation file that defines a module that contains more than one class that all interact together for this module to operate. So that's what is called physical design. And that's an additional consideration that gives more flexibility, also makes it more somehow difficult to design programs in C++. In the assignments, I will actually tell you there's going to be different parts or different modules you're going to have to implement. And I'm going to force you to actually define, for example, several classes that go in a single module or in a single file. Okay, so that's the kind of design restrictions or specifications that I'm going to give you additional consideration you have to abide with as you provide your code. Okay, so what are the advantages of separating your program in different files? First of all, it may speed up your compilation. So most compilers, or if you use make files, or when you compile different files, so for example, if you use a make file, or if you use an IDE such as Visual Studio, when you recompile your entire project, for example, Visual Studio, or if you use a make file, would only recompile the files that you have changed since the last time you have compiled this program. If you don't have this possibility, then every time you recompile, then all the code would have to recompile. Now that seems that seems not to have a big advantage, but imagine you have millions of lines of code separated in hundreds of files. If every time you would recompile everything, and every time you click compile, it may take you minutes or even up to an hour or even more if your code is very substantial. So if you can separate your file into your entire program into different files, And you have the possibility of the IDE or the compiler to be aware that it should only recompile the files that have been changed since the last compilation. Then you would speed up the compilation time. You would save some compilation time. It also increases the organization of your program. So if you organize your things correctly, then anytime you have, you're dealing with a certain aspect of your programming, let's say there's networking involved in your program and you decide to put all the networking aspects into one module that is the networking module, then you know if you have to program or fix a problem with networking, you know that this problem is localized inside of this file, okay? That assumes that you actually did this, made this decision as you were designing your program. So if you made such decisions, then it increases the organization of your program and it decreases the browsing time that you go through as you want, for example, to find a certain piece of code. If your piece of code you're looking for is in networking related, then you go to this file. Of course, modern IDEs will help you to actually navigate between all of these things, which might help, but also help if the code is divided in different files. Also facilitates code reuse. For example, following my example I just gave, if your networking component, you design it in a modular fashion, then it makes it more probable that you're going to be able to reuse this networking component in another project. So basically, you design this module here for this particular project. If you design it in a general fashion, a reusable fashion, then you increase the chances you're going to be able to take this component and reuse it somewhere else, which is, of course, saving you time and makes it so that your efforts are can be reused multiple times. Your code can be used multiple times if it was designed in a modular fashion. So it also, having multiple files facilitates code reuse, which is saving you time in the long run. So here we go and describe what is this notion of a compilation unit, which goes hand in hand with the notion. Compilation unit is something that is a term that is related to the compilation of your code, whereas a component is kind of an abstract design idea that you have. Generally speaking, these two things are, of course, interrelated, because when you think about a component, if you implement an entire component inside a single file, then it also is a compilation unit. So what is a compilation unit in C++? It is essentially one of your CPP files. So for example, when you design your program, when you code your program using Visual C++, there is two different folders. One is the source folder and one is the header folder. So your source folder should contain all your CPP files. And when you compile this project, the compiler or the IDE is going to go over the list of all the files listed in this folder, in the source folder, and then we'll compile them one after the other, okay? Of course, then, as we will see later, there would be corresponding header files which should be in the header folder. But by default, these header files are not compiled. Only the CPP files are actually taken into consideration at compile time. If you want the header files to also be compiled, you would have to have a hash include in one of the CPP files, in the correct CPP files, as I will explain later. So compilation unit is a CPP file. Okay. If you're using, for example, GCC, then what you need to do is you go GCC and then the list of CPP files that you want to be executed, okay? So it's a little bit the same as what's happening when you use Visual C++, except that you have to specifically say what CPP files you want to be compiled and become compilation units. If you use Visual Studio, it is going to go in your source file and then assume that all these files are your compilation units. So compilation unit is a CPP file. As I will mention later, also in this CPP file, you might have hash include another file. The effect of this is that it effectively takes this file and now it becomes part of this compilation unit. Okay. If this other file is also having a hash include, then this other file is also being brought inside of the compilation unit. Okay. So essentially, hash include is adding things to your compilation unit. As I will mention also a few times, if in a CPP file you go hash include a certain file .cpp, then what you're effectively doing here is you're taking this other CPP file and then you're putting it inside of this compilation unit. So essentially here you're merging two compilation units. That's one reason why, that's the reason why you should never have hash include file name .cpp, because it's merging two compilation units. The compiler is not going to tell you this is wrong, but that's something you should not do, conceptually speaking. So what a file may contain several functions, data structures, or classes. In Java, you can have, when you have a file, you have one class. And it contains all the data members and the member functions of this class. In C++, you can have one file contains several classes, all their member functions, can have a lot of different free functions, can have a main function. There can be a lot of different things inside of a single CPP file. So at the process is that when you compile your Java program, your C++ program, each of these compilation units is compiled individually into an object file. So that's what this is basically saying here. This graph is saying, so you have a set of source files. A source file, well, is a term to refer to a CPP file. CPP file and source file is the same. It's a different name for the same thing. So your program, your code, your program is composed of a set of source files. Then you have the compiler here. And for each of these source files, one object file is going to be created. Okay. Normally, when you compile these files, it generates a .o file. Maybe you're not going to see it, but the compiler is going to generate these .o files. Some compilers will actually delete these files when the compilation process is done. You can instruct it to have the files stay in your directory, but it's possible they will be deleted. So the point is that for every source file, there's going to be a .o file or an object file that is generated, which is essentially the code that was generated from this compilation unit. Okay, and each of these pieces, these are separate from one another. Okay, at this point in time after the compilation. Now, it's possible that two different object files would actually refer to elements that are implemented in the other object file. So that's why then you have, if that's happening, then you need to have the linker that will resolve these links in between your object files. Okay, that's not part of compilation, that's part of linkage, which are two different phases of your creation of the final executable. Okay, so the linker is essentially, so the linker is taking effect after these object files have been created. So object files typically have cross references. I'm going to give some examples later about that. So object files is generation of code for each of your source files. And then if these source files are referring to calling a function that is defined in another object file, then the linker will have to figure out the linkage between this function call and the function call in one object file which should be linked with the code that corresponds to the implementation or the executable for this function in another object file. You see that this is all these kinds of things that are very technical that you need to know if you want to understand what's happening, okay? Which you don't necessarily have to know when you're using Java, for example, which is good in a way that you don't have to know these things in order to make things work properly. In C++, if you don't know these things, it's going to be more difficult, or if not impossible, to understand what's happening. So, okay, so here's an example. So here I have a file, a source file 1.cpp, and I have another source file 2.cpp. And in this file here, I actually, okay, so important to understand that your CPP files, what they contain is function definitions, which contains the code that implements the functions, okay? So that's essentially what your CPP files should contain, okay? So it's possible here I have one function here called 1f, which does not belong to any class. So it's a free function. So this function here, the code is contained for this function. So when I compile this compilation unit, it would generate code that corresponds to this function. And then, well, figuratively speaking, here I have the code for my function 1f, okay? So then as this 1.o file is being generated, somehow there's a handle here that corresponds to, if you are to call 1f, then you have to use this handle and be executing this code here, right? Now you see here that there's a function af that actually belongs to my class A, okay? So that's yet another function. So there's code that is generated for this function. It just happens that it belongs to my class A. Then, similarly to 1f, there's code for my function af, and there's also a handle. If ever somewhere else I'm actually calling function af, then I would need to branch here and start executing the code that is here. Okay. As we may see here in the code of my function af, there's a call to a function bf here that is a member of this object myB, which is of type B. So essentially here I'm calling the function b : bf. Okay, we'll come back to what is meaning of colon. Colon is a scope resolution operator, which is essentially saying that af is a member of A. So here I'm calling bf, which is a member of B, okay? So essentially here in my code, when I generate this code here, this code is calling the bf function of the class B. But the bf function of class B is not defined inside of here, okay? So essentially here I have a call to bf, to bf function of class B, but it's not resolved internally because I don't have this function inside of this compilation unit. So essentially here I have, I'm looking for a handle somewhere, possibly into another, hopefully that is available in another compilation unit, that if I'm calling this function bf, that it should branch somewhere in some other code, okay? That's what the compiler at this point is supposing that's going to happen, and that's going to be resolved by the linker after. So essentially here, when you generate, the compiler generates the object file, it has some handles for things that are available to the exterior, and it is also exposing some expected handles to be available that are to be offered by other compilation units or object files. Then all these object files are given to the linker, which is going to hopefully figure out all these missing handles, such as this one, okay? So that's what happens with my compilation of my 1.cpp. when then totally separately, as far as the compiler is concerned, then compiler will compile 2.cpp. 2.cpp implements a function bf that belongs to class B. So then it would generate the code and then would make the function bf of class B available to the exterior. So here there's a handle. If somebody wants to use bf of class B, then it would be able to branch here and start executing this code, okay? So these two compilation units are made available and then given to the linker that is going to see if there are some unresolved linkage. If there is, then we'll make the connection. As we see clearly here, I'm using b.bf here in my code. So that function call, which is not available here, the function definition or code for bf is not available here. So it needs to be found somewhere else. If it's not found somewhere else, it's going to give you a linkage error. So hopefully, and in fact, there is a definition for bf here. So the linker is going to say when you call b.bf here, actually is a branching to this code here, okay? And then this actually resolves this linking, which is not going to result in a linkage error. It's going to be linked together, and then all of this is going to work at runtime. Now, this is a part about this here. What about this part here? So as we may see here in my 1.cpp, all I have is the implementation of functions. So that's what you should have in any CPP file. In general, we'll see exceptions of that as we go in further lectures. But the general idea is that your CPP file should contain function definitions. A definition, a function definition, is actually the code block that defines what is the behavior of this function, the code that defines what is the behavior of this function or the implementation of this function. So CPP file is essentially a set or a series of function definitions. Now, of course, it's possible that these function definitions refer to some types. For example, here, this function here, AF, is using a variable of type B. But B, the B type is not defined inside of here. So if I would be to compile this here and I would not have hash include here, then when the compiler goes and sees B, then the compiler would say, well, B is undeclared, and then would say undeclared type, and then the compilation would essentially fail because B is undeclared. If you want to avoid this, then probably you have somewhere in one of your files the declaration of B, which is, as we see here, we're calling a member of B, so that's a class. So we have a file called 2.h that contains the declaration of the class B, which declares the type B here. So that's why if I want B to be not undeclared, then I can hash include 2.h, okay? Okay, so if I go hash include 2.h, the effect of this is that essentially the compiler is gonna read this file here, be aware of B and be aware of C, and then when it comes here, then it will see that B is this class here and would not complain that B is undeclared, and then it would continue. Okay, so that's what's the usefulness, that's what the usage of hash include is. It allows the compiler to go into another file, read this file when the hash include is encountered. It's a little bit more complicated than that, but let's keep it this way. Basically redirects the reading of the compiler to another file at this point in time so that later on a compiler would be aware of things that have been defined or declared inside of this file. So that's why the same thing goes for A here. So I have A, so AF, so essentially here this is meaning AF is a function whose definition is given here, but AF belongs to the scope A, which is a class. So my class has been declared in my file 1.h, which contains the declaration of the class A, which contains a declaration of the member function AF. Okay, so then in order for this to work, because if I don't have this hash include here, then let's say I might have hash include 2.h, then compiler reads about B and is aware of B and C, and then this would be fine, but A is not included here, is not declared here. A is actually declared in this file here, so that's why I also need to have hash include 1.h, okay? So note that these classes that I have here, they contain only declarations for these member functions. That's something that is not something you don't have in Java. In Java, when you have a class definition, the members of this class, the member functions, are defined inside of the class declaration. So note that here I have a class declaration for my class A, and it contains only a declaration of this function AF. It does not say how this function AF is implemented. It only says we have class A, and it has a function named AF that takes an int, returns an int. Okay, it's the only thing it says. It's called a function or member function declaration. Later, we will see that you could actually put the code here. You could put a function definition inside of the class. We'll see that later. Okay, but as a basis, when you define your classes, they should most often only contain the declaration. Okay. So when the compiler reads hash include 1.h, then it becomes aware of A, becomes aware that AF is a member of A, sorry. And then what becomes aware that there's a free function 1f, okay. Then when it comes here, it knows what is A, and it knows that AF is, yes, a member of A, okay? If you would not have this declaration here, then it would only know that class A is a class, and when you would go A : AF, it would go in its declaration that it knows about A, and then see that AF is not there, and then would say AF is an undeclared function of the class A, okay? So you see that there is many more things that, or possibilities of things going wrong when you write a C++ program compared to what you have in a Java program. It's also important to know what is the linking process, what is a compilation unit, what's the mechanism involved in the hash include and so on. So that's why I'm explaining that here. It seems that it's roughly the same as what's happening actually in Java, but it is actually substantially different. But it's necessary that you understand what's really happening if you want to troubleshoot some problems you may have as you compile your C++ programs. And also do it properly, because it may seem confusing, but all of this here that I said, saying that in a CPP file, you should have only function definitions, and then in the .h file, you should have only declarations. Care that I've used the word should, okay? You could have a class declaration in a CPP file. You could even have function definitions inside a .h file. You could, okay? The compiler would not complain about that, but it would be actually bad design, okay? So C++, again, C++ gives you a lot of freedom, but the freedom also might allow you to do things which are very confusing, okay? If you would put your class declarations inside of a CPP file, it would be confusing for other people that know about how you should do it properly. If you put your function definitions inside of your .h file, also very confusing. So the standard way that everybody should understand that things should be done is CPP file is a list of function definitions. .h file is a list of class or function declarations. Okay, so basically your compilation units are separate components that you are defining. Okay, so this A file here, this one file here is one component, and this 2 CPP file is another component. These components are separately defined from one another, and then eventually as you compile them and group them together, they are using one another, but they are defined separately. They just happen to use one another at runtime. So conceptually speaking, these are 2 different components. They just happen to use one another. So your components, when you define a component, it's a concept that you define in your implementation, saying component A does ABC and component X does DEF as a part of what are the duties of the entire program is doing. Okay. As I was saying before, maybe you say, I have a component which is a networking component. Everything that's related to networking, I'm going to put it into this file, which is my networking component, which contains all the code that pertains to networking. And then that would allow me to make so that other components never actually refer to things that relate to processing using networking code or concepts. If I want to use networking concepts, I basically use the code that is defined in my networking component. So your different components are kept in several files, and then your different components are compiled separately and then linked together before the program actually runs. So this, compared to Java, you have much more freedom to define a component. In Java, you can have packages. You don't have this notion of packages in C++. You might say that putting several classes is in a single C++ file is equivalent to a C++ package. No, these are 2 different concepts. Okay, if you start trying to say this is equivalent to this, you probably be wrong along the way. Okay, so it's important you understand what is a C++ file, how does this work? If you try to say, oh, that's equivalent to this and this in Java, you probably are being wrong. So defining a single CPP file is not equivalent to say that this is, it's not the same thing as saying, as defining a Java package. So in C++, there's a separation between the declaration and the implementation of a component. As I hinted at before, in Java, you define your class, and then when you define the member functions of the class, you provide the code in the class definition, in the class declaration. So in a way, in Java, declaration and implementation is the same. Okay. In C++, we try to separate the notion of declaration and the notion of implementation. Generally speaking, declaration of a class goes into a header file, and the member functions of a class are declared in the header file, but they are implemented in the source file or the CPP file. Generally speaking, here this goes into more software engineering issues. Some of course, the software engineering students will be aware of that, but not the computer science students necessarily. So I can just go briefly over that. There's notion of cohesion and coupling. So when you want to figure out what classes should belong together in a component and what classes should be separate from one another, You have to conceptually think about how they actually relate. The more they relate to one another, the more they are using one another, two classes are using one another, the more you say that they are cohesive or that they have high cohesion. Same thing as in a sports team. A sports team, you have different players. They can do whatever they want, but if you want to win, you should have high cohesion, which supposes that everybody in the team, yes, can do whatever they want, but they're also aware of what the others are doing. And if you have a cohesive team, people will know what is each other's roles. They will have a common goal, and then they're going to be able to work together more effectively. Okay, it's the same thing for software component. You define functions, they are using one another, they trust what the others are doing, so they are achieving a common goal. Okay, that's what cohesion is. So what you want to do is to have, within a component, you want to have high cohesion, that different entities that you put inside of a component are working toward a limited set of goals. The more a component has variety of goals, the more likely it is that it's not very cohesive. Okay. You should not either also have a single entity in a component that has its own goal that is different from the goal of all the other entities in this component. So all the entities in a component should be pointing toward the same goal. Okay. So that, of course, having high cohesion increases understandability of the code because it is all achieving the same goal. If you open a file and then this file contains code that does all kinds of different things, it's more likely to be not so easy to understand, right? Also increases maintainability. So for example, if you did come back to the example of the networking component, so if you have a problem, if there's a problem with your networking, there's a bug in your networking, then you know that you have to go in this file, and actually the problem is very likely to be in this file. Also, if you want to make a change in your networking, if all your networking components or entities are inside of a single component, makes it so that if you want to change something about networking, that the change is going to be localized here. Whereas if your networking is divided across different files and each of the components are doing their own networking, and if you want to change something about networking, it's going to be more likely that you have to change any of the components that is doing their own networking separately from the others. Okay, so localizing all the networking in one file makes it less likely, if you want to change something about networking, that you will have to change a lot of files. And of course, it increases reusability. If I have a networking component, makes it, if it's well designed for reusability, then makes it more likely that I'll be able to take this component and then put it into another project and reuse very quickly the features that I had designed in this previous project. Of course, that speeds up your development process if you can use reusable components. The other, so this was about cohesion. Again, cohesion is about the fact that every entity in a component is working toward a restricted set of goals. Of course, it goes hand in hand with this notion of coupling, whereas coupling is how much links or dependencies there are between different entities. So it's possible that a certain entity will use, for example, this class here, this method is using a method into another class. So then you say that there's coupling between this method and the method that is in the other class. or if this method here is using a variable, is declaring a variable of a type that is defined somewhere else, then there's this coupling, there's coupling between this function and this type, okay? So coupling is essentially dependencies between entities, okay? So what you want to, of course, when you define a highly cohesive component, there is going to inevitably be a lot of coupling between the entities inside of a component. What you want to reduce is coupling between the different components. You want to reduce the fact that a component relies on a lot on other components. The more coupling you have across components, the more it makes it so that when you change a certain component, that you will have to change all the other components that rely on this component. So you want to reduce coupling, and you want to, so when you define a certain component, you want to make sure that all that pertains to the goal of this component is localized here, and that as much as possible that it does not also